Example, given the differential equation dc of time, concentration, dt equals r minus k times c. So c is the equation, the variable. You can give it as a variable. It's a differential equation and it's separable. We're going to find A, the solution to the differential equation, C of t, and B, we're going to assume that the initial concentration C sub 0 is less than the constants R over K, and then we're going to find and interpret the limit as time gets infinitely large of the concentration C of t. Okay, solution, we're going to separate the differential equation, and that will give us 1 over k times c minus r. Now I factored a negative 1 out when I did this, and that's dc equals negative dt. Then I'm going to take the integral of both sides, and then I'm going to get ready for a u substitution. Let u equal k times c minus r, where k and r are constants. Then du, the differential, is just k dc. Okay, let's get ready for that substitution here. And we'll have 1 over k times the integral of 1 over k times c minus r, so that's 1 over u, times, well, we have k to introduce here, a factor of k, dc. So this part is my du. So we've got 1 over u du equals the negative of the integral of dt. Okay, now I'm going to go ahead and take the integral. So, no, I'll multiply both sides by k at the same time to move the k, 1 over k, to the right side. It's going to give me the natural log of the absolute value of k times c minus r equals negative k times, over on this side we get t, because it's an integral of 1 dt, and then we need a plus constant, so we're going to call s sub 1 our constant. S sub 1 is our constant. Okay, then we're going to do get the natural log out of here by having this e to the left side is equal to e to the right side. We'll have to distribute the k. So over here we get the absolute value of k times c minus r equals e to the negative k times t minus k times s sub 1. But we can break that apart as k times c minus r equals e to the negative k times t times e to the negative k times s sub 1. Okay, and then we'll do one more thing. We'll get rid of the absolute value. K times c minus r equals a new constant that we'll call s sub 2 times e to the negative kt, with the new constant s sub 2 equal to e to the negative k s sub 1. And we'll move the r over, we'll get k times c equals s sub 2 times e to the negative k times t plus r. And then we'll divide both sides by k. We'll get c equals s sub 2 over k times e to the negative kt plus r over k. Now we're going to use initial condition to get rid of some variable. The initial condition says that when time is 0, concentration C will be equal to initial concentration C sub 0. And we'll plug that in here, and we'll get C of 0 equals S sub 2 over K times e to the 0, and e to the 0, that's just equal to 1, plus r over k. And that implies that C sub 0 is equal to S sub 2 over k plus r over k. And if we move things around, we can isolate S sub 2 over K, which is equal to concentration at time 0 minus R over K. Okay, so we're going to use that to refine our differential equation, and that will give us C of t equals, okay, replace the S sub 2 over K with C sub 0 minus R over K times e to the negative kt plus R over K. And that is good enough for the answer for part A. Now I want you to notice that for part B, we're making the assumption that C sub 0 is less than R over K. And if we subtract R sub K from both sides, that means C sub 0 minus R over K has to be less than 0. So that means that our constant, our value here, is negative. That's less than 0. Okay, and it's not, it's a constant. It doesn't depend upon time. And also, we would like to rewrite the entire equation so it's easier to understand. Concentration at time t equals this negative C sub O minus R over K. That's the part that's negative. And then we'll write this as times 1 over e to the positive kt. All right, and so what we notice about that part is that that factor goes to 0 as time t gets very large. And then we still have our plus R over K. So if I could just say what's happening here for the concentration C of t, the negative contribution of the constant C sub 0 minus R over K, that's a negative factor. That negative contribution, it gets smaller and diminishes as time gets large. Because as the time gets large, the 1 over e to the kt gets tiny. So the negative term reduces, and that means that the concentration itself, as time gets very large, gets closer and closer to the term at the end, R over K. Okay, so let's do a formal demonstration of this. We take the limit as t approaches infinity of the concentration at time t formula. That's equal to C sub 0 minus R over K times, write it as 1 over e to the kt, well that's infinity, as time goes to infinity. So this whole guy here goes to 0 plus R over K. So just as we said, that would be equal to R over K. And what that means analytically is, as the time t gets very large, the concentration C of t approaches the constants R over K, no matter what the initial concentration C sub O is. And we're done.